So first of all, I have to start with a correction. When I was teaching you about Tarjan's algorithm for strongly connected components, I actually made a small but very important mistake. And that's when I was talking about the cross edges. I said that cross edges don't matter for our strongly connected components. I was actually thinking of cross edges that go between different DFS trees. The cross edges in the same DFS tree can actually affect our strongly connected components. So I'm just going to go over this. So remember, this was our main example. I'm just going to take a small part of this graph. I'm going to take these 4 vertices, 3, 4, 5, and 6, and show you why the cross edges actually matter. So let's do a DFS on this smaller graph, and let's start it from vertex 6. So if I do a DFS here, I will have vertex 6 as my root, and then from 6, let's say I go to 3, so I will have 3 as its child, and then from 3 I go to 4, so I will have 4 as a child, and then at 4 I see that I can go to 6, but that's actually a package, right? So I have a package from 4 back to 6. And as we've seen before, the packages always create cycles. So whenever I have a package, all the edges in this, all the vertices in this cycle that was created by the package will definitely be in the same strongly connected component. But the thing that I told you last time, actually in lecture 15, that was wrong, is that cross edges don't contribute anything. And we're going to see that that's not necessarily the case. So I go to vertex 4, I see that I've seen all of the successors. So I go back to vertex 3, I see that I've seen all the successors. I go back to vertex 6, and I see at this point that I can go from 6 to 5. So 5 becomes a child of 6. Now, here's the part where the cross edges actually matter. So I'm at vertex 5 right now, and I look at the edges that are going out of 5. So they're going to 3 and 4. Let's say I consider the edge from 5 to 4, right? It's this cross edge. Now, if I just ignore this, then I would figure out that 3, 6, and 4 are in the same connected component, same strongly connected component, but I would think that 5 is in a different strongly connected component. But as you can see here, of course, all of them are just one big strongly connected component. Now, why is this cross edge actually contributing to my strongly connected component? Because, well, from 5, I can go to 4, and then I can take the back edge from 4 to 6, and then from 6, I can go back to 5, right? And the same thing would happen even if I didn't have the edge from 5 to 4, if only I had the edge from 5 to 3. I could go from 5 to 3, then take the 3 edge to 4, then take the back edge to 6, and take the 3 edge to 5. So you see, even my cross edges can be part of cycles. But what's happening here is that basically I take this cross edge, and remember, we had this property of DFS trees, which said that cross edges always go from right to left. So if I have a cross edge from 5 to 3, I have definitely seen 5 after 3 in my DFS tree. Otherwise, this cross edge would not even exist, right? So now the mistake that I had was that I was saying, well, I'm seeing 5 after 3, so it means that 5 is not reachable from 3. But that's not necessarily correct, because it's possible that from 3, I can go back to one of the common ancestors of 3 and 5, and then from there, I can go to 5. So I have to be careful about this in my algorithm. That's the thing that I have to change about lecture 15. Put it here. So I'm going to do my DFS, but I'm also going to have a stack. Okay, so I have my stack here, and I'm doing my DFS. Now, every time that I do the DFS, I would add some elements to my stack. So let's say I start my DFS from, let's say, vertex 11. So I do 11, and I add 11 to my stack. Okay. Now, when I'm done with vertex 11, I would remove it from my stack, and I would say that it's a strongly connected component on its own. And that's basically all I'm doing. I'm putting all of my vertices on the stack as soon as they become gray, as soon as I see them for the first time. And then I want to remove them when they become black, when I'm done with seeing these vertices, okay? But the really important point is that I want to remove a vertex from my stack only if it's a special vertex, only if I know that it's the highest vertex in its own strongly connected component. So can I do this? Well, let's just see what happens here. So I put 11 and I do a DFS from 11. I see that I cannot go anywhere else. 11 is on the stack. And then the DFS at 11 ends. I see that on my stack, I only have 11. So I say that my first connected component, my first strongly connected component is just 11. Now I do a DFS from 10. I put 10 here. I put 10 on my stack as well. And then from 10, I go to 7. Okay. Now from 10, I went to 7. So I would put 7 on the stack too. Now that 7 is on the stack, I continue my DFS. From 7, I see that I can go to 8. So I go to 8. I put 8 on my stack. Now from 8, I can go to 11, but 11 is not on my stack right now. So I know that actually 11 is black. So I know that 11 is completely done already. And it was like in a different tree. So 8 is actually a special vertex because 8 doesn't have any edges to anywhere else. And it doesn't have like back edges. So I'm going to say that I'm done with 8. And because I see 8 on the stack here as well, I'm going to say 8 on its own is a strongly connected component. And I'm going to remove 8 from the stack. It will make sense very soon, you'll see. Now I go back to 7. From 7, I see that I can go to 9. So I go to 9 and I put 9 on the stack. Now from 9, I have a back edge. I have an edge to 10. So I know for sure that 9 cannot be the highest vertex of its own strongly connected component. 9 cannot be a special vertex because it has a back edge, right? And the fact that it has a back edge means that it cannot be special. So when I'm done with 9, when I color 9 black, I don't remove it from the stack. So remember, I only remove special vertices from the stack. And in this case, I'm not removing 9 from the stack. So I go back to 7. Okay. Now, what do I know about 7? I know that, again, it's not a special vertex because 9 had an edge to 10. So I'm not going to remove 7 from the stack either. So I'm going to let 7 be. And then I'm going to 10. Now, when I get to 10, I know that 10 is a special vertex. So I'm going to say everything on my stack is the strongly connected component of 10. So my next strongly connected component is 10, 7, 9. Okay. And now, because 10 was special and I'm done with it, I remove 10 and I remove all of its strongly connected components. Okay. Now, but what is the rule that I'm applying here? So I said that I would remove a vertex when it becomes black and when it's a special vertex. But that's the whole point, right? Because before I had all of these things to figure out which vertices are special. I can't just say I use that. It's not going to help. Like finding the special vertices is the whole point of this algorithm. Okay. Now, the question that I want to always answer from every node is this. Is there a path from this node to another node that appeared earlier in the stack? If there is a path from this node to another node that appeared earlier in the stack, then this node is not special. Otherwise, it is special. Okay, so here's how this would look like. Let's redo the DFS from 10. So I'm doing the DFS from 10. I'm putting 10 on the stack. Is there a path right now from 10 to an earlier element of the stack? There is no earlier element of the stack. So the answer right now is no. Now from 10, I'm going to 7, right? Is there a path from 7 to any of the earlier elements in the stack, to 10, for example? No. So I'm going to continue. From 7, I can go to 9. This is my DFS. Now, from 9, I see, I put 9 on the stack. I see that from 9, there is an edge to 10. And 10 was an earlier element of the stack. So basically, you can think of it like this. I'm keeping track of this stack, but I'm also keeping track of the edges that go from right to left in the stack. So I know that there is an edge from 9 to 10 in the stack. Okay. So because of this, when I'm done with vertex 9, when vertex 9 becomes black, I'm not going to remove it from the stack. Why do I not remove it from the stack? Because, well, I know that it can reach something to the left of itself on the stack. Okay. Now, what about 7? When I reach 7, again, that's the same question. Can I reach something to the left of 7 on the stack? Yes, I can reach 10 on the stack. So I would color 7 as black, but I would not remove it from the stack. Now I go back to 10. I see that from 10, I can go to 8. Right? So I go to 8. I put 8 on the stack. From 8, I see that I can go to 11, but 11 is not on my stack. Right? Because 11 was already processed in the previous DFS, and that DFS cleared that stack. So 8 has an edge to 11, but that's not an edge to a previous element of the stack. So because 8 doesn't have an edge to a previous element of the stack, I can say that 8 is a special vertex. 8 is the highest vertex of its own strongly connected component. And I can basically say that, well, because 8 is a special vertex, I'm going to write everything in the stack up to 8. So in this case, it's just 8 itself. And I'm going to say that's a strongly connected component, and I'm going to remove it from the stack. Now I continue my DFS. I go back to vertex 10. And when I reach vertex 10, from 10, I can also go to 11, but 11 is not on the stack. I have already gone to all of the other places. So from 10, I cannot go anywhere to the left of 10 on the stack. So I say that 10 is also special. And then the vertices that are in the same strongly connected component as 10 are just all the vertices on the stack up to 10. So from the end up to 10. So I have 9, 7, and 10. I remove all of them from the stack, and I put all of them as one strongly connected component. Okay, now let's say I do my next DFS from vertex 1. So I'm going to start from vertex 1, and I put 1 on the stack. I see that I can go to 2. So I go to 2, I put 2 on the stack. Now from 2, there is an edge back to 1. Because there is an edge from 2 back to 1, and because 1 appeared before 2 in this stack, I know that 2 is not like the highest point. And because 2 is not the highest point of its own strongly connected component, I'm going to color it black, but I'm not going to remove it from the stack. And I'm just going to go back to 1. Now from 1, I see that I can go to 3. So I add 3 to my stack. From 3, I can go to 4. I add 4 to my stack. From 4, I can go to 6. I add 6 to my stack. From 6, I see that I can go to 5. So I add 5 to my stack. I can also go to 8, but that's already seen, so I'm not going to add it, and it's not on my stack, so I don't care about it. Now from 5, I can go to 3. And 3 is before 5 in my stack. So 3 is somewhere there, right? So I know that 5 is not a special vertex. 5 is not the highest vertex of any strongly connected component. So when I'm done with 5, and also the edge from 5 to 4 is similar, so I have an edge that is going like this. So I just color 5 black, and I go back to 6. Again, when I reach 6, I see that I can also reach 3, but I could also reach 3 through 5. I could go from 6 to 5 and then to 3. So 6 is also going to be colored black, but not removed. The same thing happens with 4. It's going to be colored black, but not removed, because 4 can reach 3, and 3 is before 4 in this stack. And finally, when I reach to vertex 3, I see that there is no earlier vertex in the stack that I can reach from 3. I cannot reach 1 or 2 from 3. So I know that 3 is a special vertex. And because 3 is a special vertex, I'm going to just pop the stack until I get to 3. So everything on the stack until 3 are going to be the same strongly connected component. And these are 5, 6, 4, and 3. And I'm going to remove all of them from my stack. Okay. And then finally, I go back to 1. I see that 1 is a special vertex because it cannot reach anything earlier in the stack. Honestly, it's literally the earliest vertex in the stack. So 1 is also a special vertex. And oh, by the way, 11 was a special vertex too. 1 is a special vertex, and I just pop the stack until I reach 1, and I say 2 and 1. These are also strongly connected components. Okay, so this is called Tarjan's algorithm for strongly connected components. Okay, and it's again just one DFS, and the runtime is also the same because I'm basically pushing everything on the stack only once and removing it from the stack only once as well. So my total stack operations are O n, and of course my DFS is O n plus m. So my total runtime here is O n plus m. Okay. And now we're going to code it. So in my main function, I'm first going to read my graph, of course. I don't have a color, so I don't care about this. I'm going to do a simple BFS that a simple DFS, sorry, that basically keeps track of which vertices are seen. Sin I is true if I have seen vertex I in one of my DFS iterations. Okay. And then I say for every vertex, again, you can do it in any order. For this example, I like to do it in the reverse order. If I have not seen vertex I do a DFS from I. And let me delete these parts. Okay, now let's write the basic DFS. So again, my basic DFS is that I say I have seen vertex U, and I say for every vertex V that is a successor of U, if I have not already seen V, I want to do a DFS from V. Okay. Now, what else do I need? I need to also keep track of a stack. So I'm just going to create a vector, and I'm going to call it S because it's the Tarjan stack. Okay. So whenever I'm doing this DFS, I'm going to say push the U at the end of the stack. Okay, that's the beginning of the DFS when I'm reaching U for the first time. But other than this, I want to also keep track of whether any vertex is on the stack, and if so, where on the stack is it? Okay, so I'm going to have, again, you can do it with just one variable, but I want to do it with 2. So I'm going to call it unstack, and unstack of I is true if I is currently on the stack. Okay, and then I'm going to also have stack index, and stack index of I basically tells me the index of I in the stack. So if vertex I is in the stack, where is it in the stack? Is it like at position 0, position 1, so on? So here, when I want to push back U, when I want to put U in at the end of the stack, I say unstack of U is true. And then I say stack index of U is just S.size, and then S.pushback U. Okay, so all of these 3 lines is to add U to the end of the stack. Now this part is basic DFS. And then at the end, I want to remove U from the stack. But I want to remove U only if I could not reach an element with a smaller stack index. Okay, so I'm going to also do this. I'm going to say lowest reachable index. My names are getting really large. So let's call it LRI, lowest reachable index. And LRI of I is the lowest index in the stack that is reachable from I. Okay. And of course, initially, when I'm putting something on the stack, I'm going to say that the lowest reachable index from U is the index of U itself. Okay, great. Now, when I'm doing this DFS, if I have not seen a vertex V before, then of course I know that V has never been added to the stack. So I'm just doing the DFS on V and adding it to the stack. But otherwise, I have this edge from U to V. And the question is V already on the stack? Is V on the stack? Oops. Okay, so here I'm going to say that if V is already on the stack, if on stack of V, what does this mean? This means that now U has a way of reaching some vertex that was on the stack before U, right? So I'm going to say LRI of U becomes the minimum of LRI of U and the stack index of V. Okay, that's fine. But the other thing I have to realize here is that when I'm going from U to V, and V is a child of U, V can reach somewhere in the stack, right? And that place in the stack might be before U. So I have to do this thing here as well. I have to say LRI of U becomes the minimum of LRI of U and LRI of V. Okay, nice. So now I know where is the first place in the stack that is reachable from U. But finally, when I'm done with processing U, I want to say that if I could reach anywhere before U on the stack, then U is definitely not a special vertex, and I'm not going to remove U from the stack. So remove U from the stack only if U is a special vertex. Okay, so I'm going to say if LRI of U, so the least reachable index of the stack from U, is equal to the stack index of U. So I could not go anywhere before U. Then in this case, U is special. Okay, so I would say just write found a new strongly connected component. And what are the vertices in this strongly connected component? Everything on the stack until U. So I'm just going to say all the time, take the last element of the stack. So this would be s dot size -1, and write it. And if this x was U, well, of course, also remove it from the stack. So pop back and do this until you write U. And if you wrote U, let's say write an end line and also break this file. Okay. So this will write all of my strongly connected components, and it's generally speaking easier than the previous algorithm. It's actually easier to code at least. So let me just give it the same graph as before. Yeah, and as you see, these are the strongly connected components that it found. It found 11, For some reason, it found 9, 8, 7, 10. That's wrong. Oh my God. So it found 11, and then it's saying 9, 8. So why is it thinking that 8 is also in the same strongly connected component? Is this part correct? Am I doing something incorrect here? Minimum of LRA of U and LRA of V. Stack index of V. Well, actually, in both cases, I can just use LRI of V, right? I don't need to use the stack index. Still saying that 9, 8, 7, and 10 are in the same strongly connected component. So something is happening. Again, I always have small bugs. So let's say starting DFS from U. And actually, here's the thing. I'm just going to say print stack here. And whenever I'm doing print stack, it's going to be here. The stack is, and then for everything in stack, just write this X. Okay, so I'm going to print this stack at the beginning of every one of my DFSs, actually after pushing this U. So I'm going to say print stack. And then I'm going to say I have a tree edge from U to B. And then I'm going to say LRI of U is LRI. Okay, and here I'm going to say I have a non-tree edge from U to B. And here I'm going to say again LRI of U. It's this thing, LRI of U. Let's see what's happening here. Okay, the stack is originally 11. So we're starting from here. The stack is 11. Found a new strongly connected component, which is 11, removed it. Okay, the stack then becomes 10 because I'm doing a DFS on 10. I find the tree edge from 10 to 7. The stack becomes 10, 7. I find the tree edge from 7 to 8. The stack becomes 10, 7, 8. Then I have a non-tree edge from 8 to 11. Oh, I see. I forgot to check what's on the stack and what's not on the stack. Remember, we had this Boolean as well, which said whether something is on stack. And here I'm setting it to true. And here, when I pop it, I have to say on stack X becomes false. It's no longer on the stack. And what's happening here? So here I just need the stack index of V. So if V is on my stack, I'm going to do this. Otherwise, I'm going to do that. Okay, so the problem was that I forgot to say that when I remove something from the stack, the unstack becomes false. But here I was checking unstack, right? So this check was always going true, and so my LRI values were wrong. But now it should hopefully work. Okay, so it starts from 11, finds a new strongly connected component, which is 11. Then yes, it creates the stack 10. From 10, it goes to 7. The stack is 10, 7. From 7, it goes to 8. The stack is now 10, 7, 8. But then from 8, it sees that it cannot go to anywhere before 8 in the stack. And so When 8 finishes, the first point in the stack that I could reach was 8 itself. And so it just says 8 is its own strongly connected component. Great. And then it finds 7, 9. Okay. Yeah, it found the strongly connected components correctly. So it found 9, 7, and 10 as a strongly connected component. And it found 5, 4, 3, 6 as a strongly connected component. And it also found 1 and 2 as a strongly connected component. Okay. So I can now get rid of all of these CRs that I had here. So let's do this. If I just give it the input and just look at the output, you see that these are the strongly connected components that it found. 11, 8, 9, 7, 10, 5, 4, 3, 6, and 1, 2, which are correct. And again, just as before, I want to constantly tell you that the order in this DFS does not matter, so I can do it in the other direction as well. And it would give me the same strongly connected components. So 11, 8, 10, 9, 7, 5, 6, 4, 3, and 2. Okay, so this is Tarjan's algorithm for strongly connected components. I'm going to actually give you another video for a different algorithm.